Over the next 3 slides, we apply the definition of the entropy change for the system ds equals dq reversible divided by T to the cases of isothermal, isobaric, or isochoric processes. We first consider the isothermal expansion or compression of an ideal gas. We start with the definition for the entropy change ds for a small part of the process and write ds equals dq reversible divided by T. Next, we recall that for the isothermal expansion or compression of an ideal gas, there is no change in energy, that is, du equals to 0, since ideal gases have no potential energy and their kinetic energy only depends on temperature. Using the first law of thermodynamics, we conclude that dq equals minus dw. The work for a small part of the process is written as dw equals minus P external times the small change in volume dV. However, since we need to consider a reversible path for the calculation of ds, we must express the work for reversible processes. We learned earlier that for reversible expansions and compressions, P external is approximately equal to P during the process. So we write dw reversible equals minus P dV equals minus nRT dV over V for ideal gases. So ds is expressed as nR dV over V, which by integration from the initial volume Vi to the final volume Vf leads to delta S equals nR natural logarithm of the ratio Vf over Vi. So the entropy of the system increases with increasing volume. Indeed, Vf greater than Vi implies that the ratio Vf over Vi is greater than 1, implies that the natural logarithm of this ratio is greater than 0. Delta S is therefore positive and S must be increasing during expansion. Now we consider the isobaric heating or cooling of any substance. We start with the definition for the entropy change ds for a small part of the process and write ds equals dq reversible divided by T. Next, we recall that for isobaric processes, dq is equal to dH, and dH is equal to n times CPM times dt. So ds is equal to n CPM dt over T. By integration between the initial state and the final state of the process, we obtain delta S equals SF minus SI equals integral of n CPM dt over T. Assuming that CPM is approximately independent of temperature between Ti and Tf, we can take CPM outside the integral sign and obtain delta S equals n CPM natural logarithm of Tf divided by Ti. So, an increase in temperature at constant pressure leads to an increase in the system entropy. In other words, pure substances tend to be more disordered at high temperatures than at low temperatures. Finally, we consider the isochoric heating or cooling of any substance. We start with the definition for the entropy change ds for a small part of the process and write ds equals dq reversible divided by T. Next, we recall that for isochoric processes, dq is equal to du and du is equal to n times CVM times dt. So ds is equal to n CVM dt over T. By integration between the initial state I and the final state F, we obtain delta S equals SF minus Si equals integral of nCVM dt over T. Assuming that CVM is approximately independent of T between Ti and Tf, we can take CVM outside the integral sign and obtain delta S equals nCVM natural logarithm of Tf divided by Ti. An increase in temperature at constant volume leads to an increase in the system entropy. In other words, pure substances tend to be more disordered at high temperatures than at low temperatures. Note that the change in entropy for a pure substance as a result of heating from Ti to Tf is greater when heating is carried out at constant pressure than when heating is carried out at constant volume. The reason for this is that CPM is always greater than CVM, and this reflects the fact that isobaric heating leads to an increase in both the temperature and the volume. We saw on the preceding slide that increasing the volume always also leads to an increase in the entropy.